This is Lecture 1, Introduction to Mapping and Spatial Technology. And in this lecture, we're going to be looking briefly at the history of mapping to lead into our understanding of what we might call the modern era of spatial technology. And in this era, we utilize GIS and we utilize a lot of digital data and a lot of satellite imagery. And to introduce that world that we exist in now, we'll take a quick look at the history of map making and then also some of the early attempts at doing what we would consider to be GIS, or Geographic Information Systems. So let's get started here just thinking about the history of map making. And we can think about it in two ways. One is a ladder concept, a very linear understanding of history, and a second one might be a tree concept where things that came before, they branch out and become very varied over time. And this concept of ways of organizing the history of mapmaking comes from a classic text called The Elements of Cartography. So we can look at the linear progression versus branching of the history of mapmaking. So here's an image of the branching essentially. And so we end up in our modern era with many different types of maps. So topo maps or topographical maps and thematic maps, statistical maps. These are all products that we experience day in and day out, and they share commonalities, but they are varied and they're different. And we can think of them as branches of a tree. Let's go through some of the milestones of map making. This is a very brief introduction to the history of cartography, and by no means comprehensive and complete. I'm just going to touch on some things that I think are important for us to understand relative to how we utilize GIS. So again, it's a very abbreviated understanding of the history of cartography. But given that caveat, let's proceed. So here we have a clay tablet from 500 BC, the Babylonian map of the world. And in this particular depiction of space, we see Babylon notated, and then we see elements around Babylon that were important to the culture that produced this map. So it's an understanding of space in terms of priorities, and in terms, importantly, in terms of distances, things that are away from the main thing, which in this case we can assume is Babylon. Here is a map from 1904. This is a Polynesian navigational device, and it's very diagrammatic in nature, and it's produced by natural elements, sticks, essentially, that are culled from a natural landscape. And even though it might even seem more primitive than the Babylonian map, what's important about the Polynesian navigation devices is that they're performing a function. They're allowing the user to do something. In this case, it was the direction of wind, waves, and islands, of getting from one location, navigating on a ship or on a vessel from one location to another location. So all of a sudden, maps become performative tools where they're things that help us do something in our environment. And that's a really important concept in GIS, that we're actually utilizing maps or utilizing technology around maps to solve problems. And that's a point I'll keep coming back to in this lecture, but also just in general. Here's Inuit of Eastern Greenland tactile maps, and you can see that the tactile components are on top of the reference map underneath, and the reference map obviously is a more modern understanding of space, but it has a direct relationship with the tactile components. So even though the tactile components of the Inuits of Eastern Greenland, it's still representing the same space in a valid, although it might be generalized to our eyes, in a performative way. It actually worked to represent the space in that way. So it's a very valid type of map making because it is actually able to do what it was supposed to do, which was represent space. If we think about the Renaissance, so 1569, Gerardus Mercator comes up with the Mercator projection. We can start to think about math behind maps, that there's actually a quantitative component to map making that could be really valuable. So in this case, here's the Mercator 1569 world map, and we can see that although the shapes of landmass are probably different than how we think of them now, the math behind this particular map is still being utilized today. It was a very valid type of math. And by saying math, what I'm pointing to is the actual development of what's called the graticule here. So the placement of the gridded space in the map is essentially based on a mathematical formula. And that mathematical formula for the graticule here, for the production of that gridded space, it allowed a very important thing to happen, which was navigation from one location to another location in a way that was consistent and mathematically valid. So here, what sailors needed to do with the Mercator projection is they just needed to maintain an angle across the gridded space. So as long as they were able to maintain their angle across all meridians of longitude, they were able to get from one location to another location. They still had a difficult time navigating with the Mercator projection, but it was definitely better than what they had before the Mercator projection. And they utilized what was called a Rube line. So it's a constant angle or constant azimuth from one location to another location. And although it's curved, it's maintaining the same angle from one gridded space to another gridded space within the larger graticule. This is a quick video of the Mercator projection. And what's valuable about this visualization here is that we can see that the sphere of the Earth is being described in terms of the Mercator projection, or I guess we could say the Mercator grid in a way, as a flat space. And as the space becomes flattened, we see a lot of distortion taking place in the polar regions. So we literally see the space stretching out. But importantly, the math behind the map is still valid to do the task, which is the navigational task to get navigators and sailors from one location to another location using that gridded space. So it was a new and augmented description of the Earth corrected for sailors. That's really what the Mercator projection was allowed to take place at a moment in history. And we actually use the Mercator projection still today, and it is really good for directional navigation. So we actually use a version of it, say in Google Maps, where we're trying to get from one place to another place or one location to another location. It's very valid for doing that type of activity. If we skip ahead to the early 20th century and we think about the world wars and the larger intent to modernize the century, to modernize our history in a way, the idea of creating a consistent map across all spaces was a really important concept. And map makers in the early 20th century were consumed with this idea of how do we create a consistent space across all locations on the global map. And the scale needs to be consistent, the actual look of the maps needs to be consistent, and there was a real push to produce this common vision of the world. And here's one of these, what's called the International Map of the World, or the millionth map, a scale of 1 to 1,000,000. And it had the same conventions across all space. So Boston looked like Paris. International spaces, they all shared a same common look. And although to our way of thinking, it might be a boring way to understand space. At that point in time, there was not a consistent map product available, so it became a big push to actually have that type of product. And of course, the project kind of fell apart because they couldn't get all countries to participate equally in producing the millionth map. But it definitely was a big goal in the early 20th century mapping. As we enter into our 21st century, that type of map making, we realize in retrospect, would have never really made great sense as the only map product available, because we have a rapidly changing environment, both an urban environment that's changing rapidly, but also physical features on the face of the earth due to climate change primarily. And so we need our needs are different at this point in time in the 21st century. It's not so much that we need a consistent map, although in some cases, say Google Maps, that's really helpful. We need to be able to deploy maps rapidly using a lot of data to understand a rapidly changing space. That's one of the big challenges of the 21st century, and why GIS is so relevant and so important now is because it can process and prototype and model space very quickly and easily. So let's kind of segue into what we might call our time period, or the modern era, or the contemporary era. So if we think about the late 20th century, we might want to start with Earthrise, which was from the Apollo mission. It's the first image of the Earth, 1968. It's taken from the surface of the moon from the Apollo 8 mission, and it's the first moment where we actually see the Earth from a photograph from afar. And this becomes a really important moment in the history of just imagery in general and thinking about our planet, but also it has a really interesting relationship with how we now envision the Earth in terms of the technology that we're using just a few decades later. 1968 is not terribly long ago, and so much has happened in that amount of time. One of the big things that's happened, of course, is computers. So during the late 1960s and 1970s into 80s, 90s, and now is the ascendancy of computer processing and programming and quantitative data, that this is kind of the world that we operate in now, as opposed to paper maps. Although paper maps are a product of this world, what we're really interested in is the data and processing the data from a quantitative perspective. I'm just going to play this video. This is, if we think about the Earthrise image, that was one photograph in 1968 of the Earth. I'm just going to play this video for a moment, and this is actually looking at the Earth from kind of a similar perspective and almost a certain same distance and scale almost, but we're utilizing so much more data to actually produce this particular vision of the Earth. And this is essentially using satellites at this point in time, which is a big part of the geospatial technology that we utilize now. So let's just play this for a moment and just kind of witness the scale and the breadth of imaging that we do of the Earth at this point in time.
I'm Jay Herman. I'm the EPIC lead scientist for the Discover mission. On July 6, 2015,
and one takeaway from that short video is just the scale of the data itself. So it's just, as I titled the slide here, data, data, data. And it's all being utilized for the purpose of understanding a changing landscape, or a changing world, essentially. So our project ahead of us is really to think about change and to understand it. That becomes a big task at this point in time of GIS and spatial technologies, is we're adding in a time element to phenomena that we're trying to understand on the face of our Earth. Another component is just the scale of the data itself. It's big in actual file size, and it needs to be placed somewhere. So it's oftentimes placed in a large server. So something like Amazon servers and big server farms for companies that do a lot of cloud data processing or cloud data storage. This is something that's very much a part are proprietary, and they're give out the imagery under certain licenses and for certain fees. But a lot of that imagery is available open, and certainly will be utilizing a fair amount of open data. Beyond satellite images, pretty big data sets that are available to us to utilize, and one of them that's a classic is what's called the Tiger file. And this is all the streets in the lower 48 states. This is 26 million individual road segments, and these black dots that we can see are where it becomes more concentrated and intense, and of course those are urban areas for the most part. So we can see Chicago up here, and we can see on the East Coast, we can see New York. Okay. If we zoom in close to it, we can see how dense it is and how well developed this actual product is. This is open to us. This is available. We can actually download this and start working with this in GIS and processing this data in a way that would be meaningful for, say, a project that we're working on in an urban environment, or maybe even outside of a city that's involving roads. So we have a lot of this data that's available to us at this point in time, and the great thing is that a lot of it's something that we can access. That's it's posted online somewhere. We can download it, or we can access it programmatically and utilize it in a GIS to solve spatial problems. All of this data that's being produced, both the satellite imagery and also the products, might come from satellite imagery or might come from another device, input device. These are all part of what I call the mapping industrial complex. It's a concept that I've come up with here. And the idea here is that there's all these technologies and all these companies that now have harnessed these technologies that are essentially mapping the world. And a lot of them, like Google Maps, is doing it essentially for profit. A lot of it is something that's out in the public domain that we can use. So we can use Google Maps, and we can use the productivity of Google Map, which is to get from one place to another place very efficiently. But there's sort of a profit motive behind it all also. And certainly from the government perspective, mapping space is very important. Controlling space becomes very important. Any military endeavor is highly reliant on modern maps or modern GIS, and GPS, or the positioning systems for geographic information, is also part and parcel, and they're both very important in this new world that we might call the mapping industrial complex. And of this larger complex now, there's two sides of the same coin in a way. There's proprietary software, and proprietary software is oftentimes licensed in a very specific way, and it oftentimes is expensive, and it is developed by one company, and the code for that particular product is oftentimes closed. It's not something that we can contribute to or actually even see in an open way. But these companies are very active in geospatial technology, and they are quite prominent in the industry. And so if we look on the upper left-hand corner, Esri is a classic GIS mapping platform that we would consider to be a proprietary software. It's a licensed software. And on the other side of the coin, we have what we call open source software, or FOSS, or free and open source software. And this world is also really robust. And this is, we can see QGIS in the middle, GDAL. These are open source packages that are related to GIS, if they're not GIS in and of themselves. And they're tools that are developed by an open source community. So they're developers, they're geographers, they're individuals that are contributing to the larger good of the project. This is a very active community and active space also. And the line between proprietary and open source is defined, but goes back and forth. So somebody who's using QGIS probably also knows Esri tools really well, or should. And so they aren't confined spaces. There's a lot of interplay between the two, but they do operate differently from each other. So we've talked a little bit about the history of maps, and we've talked a bit about images or satellite images, and we've also talked a bit about how it relates to our use of digital technology and computers. Let's talk real quickly about what a GIS is and the first GIS. So the first GIS is attributed to John Snow, who was a doctor who was interested in finding out what was driving cholera outbreaks. So was very instrumental in producing a map product in 1854 that's oftentimes called the Broad Street Pump Map. This map was produced relative to epidemics, cholera epidemics in London. So the 1853 to 4 epidemic claimed more than 10,000 lives. So these are really major health events that are happening in the public sphere that nobody really understood quite well what was causing them. The reigning theory was what was called the miasma theory. So the miasma theory just assumed that there was something foul or bad in the air, and that's what was causing these cholera outbreaks. And that was the extent of the understanding. There was no real quantitative parsing of data surrounding cholera events. So what John Snow did is he decided to really produce a map. And in producing the map, he was also taking a health census, interviewing individuals or households that had been affected by a cholera outbreak. And what he was able to show in his mapping and his census taking was that there was a spatial pattern relative to a cholera outbreak or a cholera epidemic. And here we can see in the map, we can see these pumps. So off to the left, there's a pump. In the middle on Broad Street, there's a pump. And right next to the pump on Broad Street is this black area. And these are coffins. These lines are actually coffin symbols. And we can see that this particular location, the deaths were extremely high. So there's some relationship that's happening right on Broad Street relative to the pumps. And we can see through the map that there's these clusters of areas or these buildings where a lot of death took place. And what he was able to find out through the actual production of the map and also the census taking behind the map was that those locations where there was a lot of death taking place away from the Broad Street pump, they still used in their daily activities the Broad Street pump. So they had a relationship with that pump, even though it wasn't on the first pass completely evident. Through the information behind the map, he was actually able to understand the phenomena, and he was able to understand that that pump on Broad Street was what was causing the actual deaths. So there's a causal relationship. There was a correlation between the deaths and the actual pump. And within this larger mapping framework, he was able to develop that finding. And so this is kind of the first moment where a map, the actual data that's going into the map, becomes really critical to solving a health problem, but also a spatial problem, understanding the health problem in terms of spatial dynamics. So it's different than, say, the Mercator projection, where the Mercator projection is a navigational map that's helping us get from one location to another location. This particular map is helping us understand a phenomena between variables. And in this case, the phenomena between variables is getting water at a pump and deaths that are taking place as a result of that activity. So we might call this a proto-GIS, an information system that's in map format that's giving us back really useful information. And we can test his findings using tests that we would do in GIS. So here we can see we have these service areas, these polygon service areas that really are very similar to John Snow's original map. So using the original data, we can see that even when we run it through a modern GIS, we start to get kind of these neighborhood effects. So P7, which is the blue points here, those all kind of share what we could call a neighborhood. Or same difference between what we would consider to be an actual walking distance. we can see that we have neighborhoods, and again, P7 here is a neighborhood. All those blues, they're sharing a commonality in the space itself. And so the walking paths really reflect what John Snow was finding in his findings also. So we're just testing it in a modern GIS, and in fact, we can show that his results are very valid from the original study. This brings us to one important GIS concept about proximity, about things being close to each other, and things that are close to each other tend to relate to each other very well. So near things are more related, are more similar than distant things. So when we're doing GIS, we're constantly thinking about distance, and we're thinking about patterns, spatial patterns within our mapping. How do certain things relate to other things? And one of the big laws is that if we see some things that are very similar, that share some commonalities, they're likely clustered. They're likely close to each other. And the law states that as things dissipate or as things are farther away from each other, they may not share the same characteristics in the frequency that you would have with things that are close to each other. So that's one thing that we want to always think about when we're dealing with GIS, is this law of geography, which is about proximity. Let's think about a modern day GIS, what we're going to be utilizing, where it came from. So the first really modern GIS, beyond the concepts that John Snow uncovered, which is variables or data existing in the same space and forming a relationship. Let's think about how we actually have what's a modern day GIS, which is basically a computer-based system. So that really came out of the late 1960s from work that was done in Canada by Tomlinson. And Tomlinson was able to take the map sheets that were produced by the Department of Forestry and put them into a computer system, digitize that data, and actually produce a whole world of these maps that was accessible via a computer. And of course, having it accessible within a computer then allows you to query the data. It allows you to understand the data in a more sophisticated way than just looking at maps. So this was the first moment where using some of the principles that John Snow kind of stumbles upon, utilizing that within a computer system. And of course, that advances over the next decades to get us to what we would consider to be a really contemporary GIS system like QGIS or Esri. One commonality between all modern day GIS systems is that kind of operate by principles. And there's 4 really critical principles that I want to introduce, and then 2 guiding concepts. So the rest of the lecture here is going to cover these 4 principles and these 2 guiding concepts. And these are really things that we just want to kind of keep in mind as we're starting to work in a GIS, because they're the benchmarks of the whole system. That if we understand these concepts, it's going to help us understand what's happening as we're actually doing work within the GIS framework. So the first principle that I'm going to introduce here is called stacking or GIS layers. So here we can see an image. So on the bottom, it's what's called a DEM, or a digital elevation model. And then we can see after that is it looks like what's called an orthophoto, or a image. And then on top of that, we can see what are called polygons, the red and the green. So those look to me like they might be what's called a buffer, the red area, and the green might be what's called like a land use. That might be like a forest cover. And then the blue lines on the very top, those look like rivers or waterways. And then the yellows, they might be points of interest. Maybe they're locations where we've taken data samples from. But what's important is that this data is thematically organized across the layers, so each thematic is different from the other ones. And importantly, they're located within the same space. So they're literally stacking upon each other in the exact location that they exist on within the model. And the model, of course, is referencing the actual world. So a GIS system uses the stacking principle to thematically organize across different layers of information. And importantly, all that's referenced to actual space. So the GIS layers are a model, a very effective model of actual space that exists in our world. And so here we can see the stacks in a more diagrammatic way. These stacks are sitting on top of each other. And importantly, the themes stay separate. So everything that is about land use, maybe it stays on one layer. Everything that's about certain locations, it's on another layer. Everything that relates to, say, an image, like a satellite image, that stays on another layer. So we can keep the layers separate, but they can be in the same space together. So that's that concept of stacking, of GIS stacking. The next principle, the second principle, is what we call spatial data versus attribute data. So spatial data and attribute data, they kind of go hand in hand and they relate to each other, but they're different. And the spatial data component of GIS data is what we see. It's the actual map components that we see on the screen. And these oftentimes have associated with them within the GIS system what we call a attribute, or a attribute table, or a tabular view. So let's walk through this particular instance here. So here we see in the geographic view at the top, there is a yellow parcel. So we're assuming this is like a neighborhood and this is the end of a cul-de-sac. That particular area has a PIN number. So it's 334-1626-004. And that is owned by somebody. It has a certain square area. It's been assessed at a certain value. And all those attributes, all those components of that thing that we're looking at on the computer screen or within the GIS, those are what we call attributes. And they're held in a table, essentially. And of course, we can query that table and utilize and access that data readily with using a GIS. So just as long as we keep in mind that the thing that we're seeing on the screen is different than all the data behind it, but they're related in interesting ways, oftentimes joined. As long as we understand that concept, that sort of spatial data versus attribute data, that's really helpful. Another concept to keep in mind, a guiding principle, is vector versus raster. And we'll use this term quite a bit, of vectors versus raster data, and we need to just understand that these are models of space. So the vector model rests on points, lines, and polygons, and the raster model rests on a gridded space, and there's a value that's held behind each grid or each pixel within the space, and that's called the raster model. And we can see on the screen here that we can represent the same feature, we can represent the same real thing in life. So in this case, maybe it looks sort of like a cul-de-sac. Maybe it's a lake surrounded by a road. I'm not sure exactly what the feature here is that we're looking at, but we can see that we can represent it two different ways. So in the raster, we can see the blue area, which is similar to what we see in the vector also. We oftentimes call raster bitmaps or raster data, and then we have vector data, and then we have this term called geodata. And everything in vector and everything in raster that we're utilizing in GIS is going to have a coordinate system, and it's going to be on a y-axis and an x-axis. When we introduce a geographic or a geodetic space, the space of our world, we start to use the term geodata. So both raster and vector can be geodata as long as they share a coordinate space that makes sense for modeling the world. And one of the most common, and the one that we're going to be dealing with very soon in our first week here, is latitude and longitude. So latitude is the y-axis and longitude is the x-axis in this particular coordinate system model of the Earth. Now, both vector data and raster data can exist in the same space together in a GIS, and they can represent the same features within the model. They just do it in two different ways. So again, raster is all about the grids, so that's the gray grid as the black line goes through it, and the black line itself is the vector. So just remember, we can have vectors and rasters in the same space. They just operate on different principles. The next concept and the final concept is coordinate systems, or coordinate systems and spaces. And when we're working in a GIS, usually using what's called a coordinate system that has reference to the Earth. And a classic one that is probably the most dominant is latitude and longitude, or a geodetic coordinate system using latitude and longitude. And again, it has a y-axis and an x-axis. And it's similar to a graph space of an x-axis and a y-axis. But in this case, what we add with latitude and longitude is we add a graticule, which is the gridded space of the Earth, onto a round sphere. And in this particular model, we use a point, a fictitious point in the middle of the Earth, and we draw out angles. So every point that's sitting on the face of the Earth has an angle of latitude, and it also has an angle of longitude. And these are degrees of latitude and degrees of longitude. So for the east coast of the United States, the latitude is approximately 40. So we can see that our latitude line in this particular graphic is pointed towards the east coast, the northeast, and we're in the 40s there. And in terms of longitude off the coast, we're in the 60s. Okay, so it's going to be a longitude of approximately minus 60 or 70, and a latitude of approximately 40 or 50 or so. And this way we can actually describe locations on the face of the Earth using two things, latitude and longitude. And here we can see another demonstration of that graticule or gridded space. And here we can see the prime meridian, which is the 0 degree, and then also the equator, which is the 0 degree in terms of latitude. And prime meridian is related to longitude. And as we go around in terms of longitude, we start off at the prime meridian, go across Europe, across Russia, go to the back side of the Earth, and then we come around and we're into negative longitude at that point in time. So as we come across the United States, we're using a negative longitude. In terms of latitude, we go degrees north of 0, north of the equator. Those are going to give us positive numbers. And as we go south, towards South America from the equator, we have degrees of latitude that are minus. And we can also describe it in terms of northwest, southwest, northeast, southeast as 4 quadrants. And each one of these 4 quadrants shares a latitude and longitude pairing. So for North America, for locations in North America, it's going to be a positive latitude, a minus longitude. South America, both are going to be minus. For Europe and parts of Africa and Asia and Russia, we're going to have a positive latitude and a positive longitude. For Australia and countries in the southern hemisphere, let's go back to the last slide, that is in the southeast, we're going to have a minus latitude and a plus longitude. There's one particular location that's unique of all other locations, and that's what we call, in a joking way, Null Island. And this Null Island actually doesn't exist. It's just a location of 0, 0. So it's literally off the coast of Africa, and it's the origination of the prime meridian in the equator. It's 0, 0. So it's kind of a joke. But what's interesting about it is that in GIS mapping, oftentimes we'll have data that will end up as a mistake, and it oftentimes defaults to 0, 0. So oftentimes you get a lot of points out in the middle of the ocean off the coast of Africa. And usually you know that something's gone wrong when you have 0, 0, because it's not really representing a location that makes any real sense to anyone. But I thought I'd just mention that because it helps us understand that there's an origination point of this whole system at 0, 0. Beyond the 4 principles of GIS that we've talked about, there's 2 big concepts that we need to think about also that apply to any type of mapping endeavor. And the first one is scale. So we're going to be dealing with scale quite a bit in producing maps and working with data in GIS. And the terms that we use are large scale versus small scale. Using these 2 terms, large scale versus small scale, it's relative. So there isn't a threshold that we cross that gets us into large scale or gets us into small scale. It's a relative term. And for somebody who's a, say, urban planner, large scale may mean something different than it does to somebody who's accustomed to just mapping at, say, a global scale. Generally, large scale is related to mapping where we can see, where we're very concerned about buildings and roads and parks and locations that are very much a part of our world, that are close to the face of the earth. Okay. With small scale, it's more from a regional perspective or even a global perspective. So the actual entities, the buildings and the roads, they might not be as important, but what's more important is a more global scale or a more regional scale where we can see all roads or we can see all urban areas within a certain region. And that's what we would call a small scale mapping. So I just want to introduce these 2 terms right now. We'll get more into detail about what these mean and how they are utilized in GIS. But keep them in mind right now as large scale versus small scale is a big GIS concept. We also, especially when we're dealing with the vector model and mapping in terms of latitude and longitude, is we're dealing with decimal precision. So each pairing of latitude and longitude is going to have a certain degree of precision. And depending on what we're doing, we can either put up with low precision latitude and longitude, or we really need high precision latitude and longitude. So if we want to know exactly where the Statue of Liberty is and exactly where all the particular locations are in the map that we're producing in terms of points, we need to have high precision. And the way that we derive high precision is we just use the decimal places to produce that high precision. So in this case, if we want to have a precision of, say, 1 meter, we need to have at least 5 decimal places after the decimal point. If we just want to get a point that represents New York versus Boston versus Chicago, and we really don't care if the point's actually on the Statue of Liberty, then we can put up with a lot less precision in our decimal points for latitude and longitude. So in this case, even 40.7 comma minus 74.0 is going to get the point somewhere within New York City. So this brings us to the end of Lecture 1, Introduction to Geospatial Technologies.